Again, can we have any volunteers that are willing to present? Yes, okay. Raj? Okay, let me go ahead and pass it to you. Okay, so Raj, can you talk or not? Raj, can you talk?
Hear me?
Yep, perfect.
Okay, pretty sure this is the answer right here.
Okay, and can you explain how you got that?
Well, the standard equation is EA is equal to Q over epsilon naught. So
Right.
we know that Q is equal to the density, charge density times the volume, so we substitute that, and we know that it's because it's inside this, and it's a solid non-conducting cylinder. We have to use the volume proportion, so that's over here. So we had the pi r squared times h over pi r naught squared times h, and we just took it out, and that's r squared over r naught, or yeah, r naught squared. And then after taking out the necessaries, it ended up the charge density times the r value over epsilon naught times 2.
Okay, now wait a second, Raj. So I agree that you said the charge is equal to the density times the volume. And so it looks like you found the ratio of the volumes. So I'm looking at that for a second. So I just want to see how you're canceling things. So the pi's cancel, the h's cancel. And so now I'm looking at the numerator kind of upward to the right of your final answer. And where did that other, when you have the rho times the r naught squared and you canceled it out, where did that r naught squared come from?
This one?
Yeah.
This is not the, wait. Oops, there's other variables to it.
Okay, so Raj, interestingly enough, you've got the right answer, but you didn't do it the right way. So it kind of looks like you have two wrongs making it right. So let me go back to kind of in the middle. That's very important where you have Q equals the rho times the volume. That's exactly right. You don't have to do a ratio of the volumes here. All you have to do is take rho times the volume. And Raj, will that be the volume of the entire cylinder or just the volume of the Gaussian cylinder?
Could you rephrase the question?
Well, we want the charge that's enclosed, right? So
yeah.
When you do rho times V, will that V be the volume of the entire cylinder or will it be just the Gaussian cylinder?
The Gaussian?
Yeah, just the Gaussian. So when you say volume equals pi r naught squared times h, that's not exactly true. It's just pi times r squared times h. Okay? And then you would divide both sides by the area, which is going to be 2 pi r times h. The pi's will cancel, the h's cancel, one of the r's cancels, and voila, you get your answer there. Okay?
Yeah.
So I'm going to transfer over to somebody who has the exact same answer, but I think they did it differently. I think, Michael, I think I stopped in and saw yours, so I'm going to see if I can you and see if I can pass it to Michael. Let's see. Okay, so let's look at. I think he did that. So Michael, can you talk? So he can't talk, but we can look at his. Okay, so let's look at his. You'll see that he's got rho times pi times r naught squared times h all over E naught times the area, which would be 2 pi RH. The pi's cancel out, the h cancels out, and there's only one mistake that I see here, and that he put an R naught instead of just being an R, because it's not the entire cylinder, it's only the Gaussian. Oh, I'm looking at the wrong one, aren't I? Oh, okay, sorry. This is what happens when I try to explain somebody else's work. The pi's cancels, the h's cancel, the r's cancel, and so we get the exact same answer that Raj had. Any questions? Okay, thank you very much. I'm going to take it back from you. Okay, so now what I'd like you to do is I would like you to do number 10 here, where you're plotting the E versus R. So I'm going to give you a couple minutes to do that, maybe only a minute. Is anybody willing to present their graph, their sketch? Kurt, let's see. Let me see if I can pass it to Kurt. Okay. So Kurt, can you talk or no? No, can't talk? Okay, so we're just going to have to look at his graph. So what do you mean by not inverse? Can you describe not inverse better, please? Linear, okay. I'm not sure if everybody could say that, but that's a linear relationship. And then he has this as being an inverse relationship. Kurt, I can't really draw on your whiteboard there, but what I would like you to do is, do you see where the inverse meets the linear? I would like you to figure out what is that y value there. So if you draw a dotted line, a horizontal dotted line over, I would like you to tell us what that y value is for the E field. You can write it down or something. Here's your hint, Kurt, if you're really struggling with this. The value you got for A has to be equal to the value at B there. So, and you know what your X is. Your X is given on the graph. Okay, so when are those two equal? What would R be equal to? Because I see R in both of those. What is R equal to? R naught, right? Okay, so could you plug R naught into, it's probably easier on the bottom equation there. Yeah, so go ahead and plug it in. Can you write R naught there? There you go. So, and then scroll back down to the graph so we can see it. So that's what that value is over there. So on AP tests, sometimes they'll want you to put in, what is that, it's not an inflection point, but that maxima, there you go, that maximum E value. Okay, any questions from anybody? Okay, I'm going to reclaim the rule. So now what I would like you to work on is, actually, you know what? I would just like you to follow me because I want to get caught up. We're going to do a little bit of notes here. Okay, so I'm going to actually skip this one here, the one that's a ring, and I'm going to jump down to this one where it says, by the way, if you're wondering what worksheet this is the field comparison worksheet, page 4. So I'm going to jump down to the one where it's between two concentric spheres of mass, and actually it's not necessarily between two concentric spheres. It's just simply I need to open this in the Twidless site. Sorry about that. Let's see. Give me a second. Okay. So I'm going to kind of sketch here what we're looking at. So for this one, we're looking at two concentric spheres. And I'm not just talking about in between them. I want to know it in all regions of space. Okay. Well, it might be hard to imagine two spheres of mass here. But we did this one the other day between R and 2R and 2R. And somebody shout out, what would the E field be at when you're inside in the middle here? So less than R. What's the E field going to be? 0. Okay. So there's that. And I'm going to jump way out here outside. If this has a charge of little q and this has a charge of, let's say, big Q, I don't really care about what the equation looks like, but what kind of relationship is it way outside here? Linear, inverse, what is it? Yeah, you're right. The total charge would be Q plus little q. But I want to know what the E field is. Is it an inverse? Eli says just inverse. How many people agree with that? So way out here, it's just an inverse relationship. I have inverse squared, inverse squared, inverse squared. Eli, a bunch of people are saying inverse squared. What do you think? Okay, Eli says it's possible inverse square. Well, keep in mind, Eli, that the way you would figure out the answer is you use Gauss's law again. And that's E field times A, dA, equals Q enclosed, which Raj and everybody else said would be Q plus big Q over epsilon naught. And this area is going to be 4 pi r squared, right? So when you move it over, it would be an inverse square relationship, right? Okay, so it's going to be inverse square out here. I'm going to go ahead and go back to yellow. It's going to be an inverse square relationship out here, something like that. What about in between R and 2R? So you're in this region right here. What kind of relationship would that be? Type it in. What kind of relationship? Inverse square again, right? So maybe something like that. Okay. Any questions about that? So then what would if I had two shells of mass then? So we have some strange planet. Aliens are playing tricks on us. And then there's this inner shell of mass. What would the relationship between the gravitational field and R be? We have R again, and we're going to have 2R. How would it compare to the graph I just drawn over here? How would it look? It looked the same. Okay, good. All right. So an inverse square, inverse square. Okay. All right, now I want to come up to this one. Okay. Any questions? Considering that the charge is different, would we have drawn the inverse square differently? No, I mean it's still going to be a relationship of true. You could have a charge that's attractive or repulsive. Ben, yes, you do have this paper. It's the big packet. But whether it's attractive or repulsive, it doesn't matter. Now, if one's positive, like if big Q is positive and little q is negative, then yeah, it would look a little bit different. Right? Yeah, Michael, right? It would look different if the polarities were different. Like, for instance, if little q was positive, or excuse me, big Q was positive and little q was negative, then this would flip down here. All right, so now I'm going to come up here to the ring of mass. So imagine we have this ring of mass, like this. So it's like a donut shape of mass. And this is all filled in. I'm not going to draw it all in, but I'm some distance away. And I have this point P here. And I want to figure out what the gravitational field is from this ring of mass. Can you see there would be a pull this direction to some of this stuff over here? There would be a pull this direction from some of this stuff over here. And same thing for all of it, right? Can you guys see that? Yep. Okay. And I want you to think about if this would be a ring of charge. So we're going to be comparing that to the E field created by a ring of charge. So a bunch of, let's say, positive charges or something like that. Okay. And again, I have a point P, and I want to figure out the E field from it. Okay. Can you see that the answer to this is going to be very similar to for the mass? Can you guys see that? Yes. Okay. So that's really what my whole comparison here is. I want you to compare those two fields at all times. Now, the last question I have for this worksheet is, can I use Gauss's law to help me here? Think about all the other Gauss's law problems we had. For this one here, you drew a Gaussian pillbox, Gaussian pillbox that mirrored the geometry of the situation they had, right? So in other words, you drew a cylinder, okay? And that helped you because you wanted to find the, let's say, the charge, or not the charge, the E field right there, or wherever, okay? And it is very symmetrical. This is also symmetrical. I think you guys can see that, but I want you to think, can a Gaussian surface help you figure this out? Michael said something, you need the volume of a ring and surface every ring. That's true, Michael, but I do have a question for you. If I'm over here, do you see how my whatever Gaussian surface I would be drawing in here, another ring, let's say, that I'm going to have a field in this direction and a field in this direction on that ring? So what I'm trying to get you to see is that Gauss's law has its limits. It's very helpful for a very symmetrical situation. In fact, very simple geometries. But in something like this, Gauss's law is not going to be very helpful because we're going to have two different pulling directions. Even when I draw my Gaussian shape here, I'm going to have a pull in both directions, or in two different directions, or actually many different directions because we have the charge distributed uniformly throughout. Okay, so if Gauss's law doesn't work here, what would I have to do? What was the harder way that we looked at? Right, that's right. We're going to have to do calculus. We're going to have to integrate Coulomb's law. Yes. And that's pretty hard, right? Yes. So we're going to save this one to class. Mr. Lenfest is going to work hard, and you guys are going to watch us. But you would definitely need to know how to do something like this on an AP test. Sounds good. All right. All right, moving on. And I'm trying to get caught up in notes here. I would have you guys whiteboard this. Question? No questions. Okay, so I'm supposed to draw many gravitational field vectors. I'm moving on to the gravitational fields and equipotential surfaces sheet. So for this one, I have this picture here, and I'm supposed to draw in many gravitational field vectors. So tell me, how would I do that?
Parallel and straight down.
Parallel and straight down. Thank you very much, Puneet. So that's my attempt at drawing a parallel line, and I'd have lots of them, and they'd be nice and uniform, right? They're not going to be concentrated in one section and sparse somewhere else. Now, I'm not going to waste the time to draw all these in, but can you see that it's nice and uniform, especially if I draw them nice and parallel? You guys are okay? So those are my gravitational field vectors. So those are my gravitational field vectors. Now look at number 2. Fields are abstract constructions. So it's not like you can actually look around in your room right now, stop looking at the screen, look around the room. It's not like you actually see arrows pointing down toward the center of the earth, okay? Those are abstract mental constructions that people have created to help us, you know, do calculations and solve for things. And specifically, how they're helpful is they deal with vector phenomena. Vectors. Easy or hard to deal with vectors? Hard, right? They're kind of a pain because sometimes they're in one direction, sometimes they're in another direction. Sometimes you have to add vectors, sometimes you have to subtract vectors. And it's not easy addition and subtraction. You have to use Pythagorean theorem to figure it out, right? So I want you to think about last year. Last year we did kinematics, which was vectors. You guys got really good at it, but it was, you know, it was kind of a pain in the beginning because there's a lot of vectors going on. Now we try to make it easier. We try to have one dimension, but eventually we did two dimensionals, and it kind of got to be a pain. But do you remember near the end of the year, we didn't have to worry about vectors anymore. There was something that was a big idea in physics that helped us solve problems that we didn't even have to worry about direction. So for instance, if you're throwing a ball and you know the initial height and you know the initial speed, if you know the final height, you can figure out the final speed. What was that thing that we learned? Yeah, energy, right? Energy. So the next thing is going to be related to energy. Equipotential surfaces are also abstract constructions. They're utilized to explain scalar phenomena, which are more friendly. Okay, those are easier to deal with. We don't have to worry about direction so much. An equipotential gravitational surface consists of all the points in space where the gravitational potential energy per unit mass is constant. Okay, I need to draw on some gravitational potential surfaces. Again, what a potential surface is, an equipotential surface, is where all the points on that surface, on that line, the energy is constant. So how would I draw an equipotential surface on the picture up here?
Horizontal?
Horizontal lines. Thank you very much, Puneet. So horizontal lines. And this is my best attempt at drawing a horizontal line there. And I'm going to draw lots of them in. So I'm going to try to do it equal spaced. Doing the best I can. And there's another one. Okay, so then it says in number 3, label the gravitational potential surfaces P1, P2, P3, and so on, with P1 closest to the ground. So this one here is P1, this is P2, this is P3, up here. Okay, how does P1 compare to P3? Let me look at the picture again. So P1 is bigger than P3? Oh, it's less than. Which one is it? I'm confused. You guys are confusing me. Is P1... Ooh, we're getting a fight going on. Ooh. Somewhat funny. Keep in mind that we're trying to figure out the potential, and it is definitely related to energy. All right? So is the energy going to be greater at P1 or is it greater at P3? Raj, I like how you're being honest here. So I kind of want Raj to answer this. Is the energy more at P1 or P3? Raj, is the gravitational energy more at P1 or P3? Raj, yeah, it's more. So that means that P3's got to be bigger than P1, right? Okay, so P3 bigger than P1. Oops, can't hardly see that. P1. Feel better about that, Raj? Does that make sense? Raj not saying anything. Does that make sense that the energy, it's higher up? Does it make sense that if it's higher from the ground? Okay, all right. All right, so what's the relationship here? So what can somebody tell me here? If I'm trying to figure out P1 has got the lower energy than P3, so what's the relationship here? How can I figure out where the greater potentials are? Looking at my picture here. Further away, right? Further away. In fact, look at the relationship between P1 and P3 and the gravitational field vectors. Notice that to get greater energy, do I go with the vector or do I go against the vector? Against the vector, right? Okay, so I'm going to go ahead and write that then. I'm going to say that, in fact, I'm going to type that, it'd be easier. Moving against vector, actually G field. How's that? G field. You increase in potential energy. Okay, then the next one here says, what do you notice about the scalar equipotential surfaces in relation to the vectors? So here's the dotted lines for the equipotential surfaces and the field vectors. What do you notice about those two? Michael says they're perpendicular, so does Mike. You guys see that they're perpendicular to one another? Yes. Okay, so I'm going to put that down then. Perpendicular. Okay, then number 5, an object of mass m falls through a potential delta P above. How much work does the gravitational field do? Notice that it says here the equipotential surface is related to the energy. So in other words, I'm not sure if I can write this or not. I think I'm going to have to draw this. So therefore, in other words, the change in potential would be equal to the change in energy. Now be careful, this E is not the E field, that's energy. In fact, maybe I'll put a subscript G here. Gravitational energy per unit mass. I think that's what it was kind of defined above as. Let me go back up so you can look at that. It says an equipotential gravitational surface consists of all the points in space where the gravitational potential energy per unit mass is constant. So if I want to change my potential, go from one potential to the next, there's going to be a change of energy because the mass is constant. Okay. So one more thing, though, I want to look here. Do you see that when I go from P3 to P1, I'm decreasing the energy? When I go from, if I were to drop, yeah, so when I go from P3 to P1, I decrease in energy. But when I figure out delta P, I do delta P here, which is going to be P1, it's always the final, minus P3, right? It's always final minus initial. Can you see that's going to be a negative? Because P1 was less than P3, right? Can you see that that's negative? Yeah, okay. So if that's negative, I want to come back up here. The change in gravitational energy, though, how much work, that's really positive, right? So I'm going to put a negative here, okay? The negative change in that potential, because if not, I'm going to get a negative. I hope you saw that delta P is negative, but the amount of work that it's doing is positive. And maybe I need to go back up and explain better. The force of gravity is this way. The force of gravity is down when the rock's falling, and it moves downward, D. So can you see the amount of work that gravity is doing is positive? The force is down, the displacement's down, it's doing positive work. If you push something across the floor and your force is to the left and the displacement's to the left, you're doing positive work. Does that make sense? Okay, good. But can you also see that my delta P would be negative? So in order to get rid of that negative sign, I'm going to put a negative right here. Okay. So this is going to be equal to the work, because work is change of energy. If you're like, well, what's going on here? Remember, work is change of energy. So that means when I solve this, I get negative m times delta P is going to be equal to the amount of work that we do, W. And again, the reason I put the negative there is because delta P is going to be negative. This way I'll get a positive number. Okay, any questions? Okay, moving on then. It says on an alien planet, an object falls towards its surface. What would you need to know in order to calculate delta P? Gravity, yep, you need to know the gravitational field strength, right? That's one thing you need to know. Okay. You need to know the mass of the thing. What else would you need to know? Yeah, you need to know that, I'm going to, instead of calling it height, Michael, because really it's not necessarily the initial height or the final height. What is it? Is it radius? No, wait a second. Yeah, it's a change, right? I'm going to call it distance. Is that okay if I just call it distance? Is that okay? I don't know what that means. Yeah, okay, I'm going to call it distance. How far it moves. Okay. So I'd need to know those things, the gravitational field, the mass, and the distance. And so, okay, so what would that delta P look like then? Well, I know that the work, which is equal to the change in gravitational energy, is going to be equal to that mass times G times, I'm going to call it D for distance, okay? So keeping in mind that this negative delta P would be related to this change in energy, I need to kind of put that in here, that this negative delta P is going to be equal to this energy right here per unit mass. So can you see that the change in potential energy is going to be equal to the, whoops, not the mass. It's going to be equal to the gravitational field strength times the distance. Yeah. Does that make sense? Are you guys okay with that? Yes, no, maybe, yes, okay, all right. Okay, let's go down then a little bit further here. Okay, I'm going to finish up at 20 after. I'm going to go right up to it. Okay, the picture below is of Earth, drawing many gravitational field vectors, drawn as, okay, so just draw the gravitational field vectors. Tell me how to do that. Arrows pointing inward, okay? So I'm going to go ahead and draw the arrows pointing inward like this. So there it is. Doing the best I can. And, okay. And then you guys probably already typed this, but, oh, right there. And then they get smaller farther out. So I wanted to ask this question here. Let's say I'm out at a distance r, and this is the gravitational field vector. You can see the length of it. What if I were to go out 2r? How long will this vector be? 1/4 the size. Any questions why it's 1/4 the size? Okay. What if I was going out 3r? What would the size be? 1/9. Okay. All right. Any questions why? Okay. Let's see here. Okay, now I'm supposed to draw in gravitational, where am I? Gravitational potential surfaces. So I'm going to use a different color here. I'm going to use red. I need to draw in equal potential surfaces here. Somebody tell me how to draw concentric circles, okay? And let's go back to the reason. I'm not sure if everybody was able to figure out why. The reason is because remember how we said that the potential surfaces are always perpendicular to the field. So when I come down here to draw a potential surface, at this location here, it's going to be perpendicular to the field. Over here, it's got to be perpendicular. Over here, it's got to be perpendicular. And over here, it's got to be perpendicular. So it's everywhere perpendicular. So that means it's going to be a concentric circle. And I'm going to draw another one out here. I'm doing the best I can at drawing concentric circles, which is not very good, but bear with me. It wouldn't be any better in a classroom either, so I guess I could always lie and say it would be better, but it wouldn't. It's not bad, actually. Okay, so there they are, and I'm going to label them. This is P1, and I'm going to skip P2, and this is P3. And P infinity would be way out at infinity, okay? So the first question is, as an object of mass m falls from P infinity to P1, what happens to the potential energy? Okay, I got two things. I have increases, decreases, decreases, increases, decreases. Okay, I'm getting lots of different answers. Okay, I'm getting, most people are, I'd say about 2/3 of you are saying decrease and 1/3 of you are saying increase. I don't want you to think about an equation. I'm a little bit worried you guys are thinking of equations. I want you to think about up here. Okay, what happened to the energy as we went from P3 to P1? What happened to it? It got less, right? So down here, if we're getting closer to the surface, what's happening to the energy? It decreases, right? So this first one's decreasing. Now, if you guys are knowing formulas already, it's going to lead to confusion, okay? So the answer is decreases. I'm hoping that you guys see that it's kind of logical based upon what we've done so far. What happens to the kinetic energy, by the way, as it falls? It increases too. Now, so for the people on the last question who said it increases, can you see why that's a mistake? Because really, if you had something falling, you'd be saying, oh, wait a second, potential energy is increasing and the kinetic energy is increasing. Well, wait a minute, that can't be, right? Okay. Okay, because of conservation of energy. Okay, let's move on to the next one. Getting close to the end. What happens to its speed as it falls? Increases. Okay, get ready for a trick question, maybe. What happens to its acceleration as it falls? Some people are saying constant, some people are saying increases. Okay, let me ask the next question, actually the last question here, because it might be easier. What happens to the gravitational force as you get closer to the Earth? Increases, okay. What happens to the gravitational field as you get closer to the Earth? Look at my black arrows. Increases. So now let's go back. What happens to the acceleration as you get closer to the Earth? Increases, right? It's only constant when we're looking at a surface where we have a constant field. But here, can you see the field is not constant, it's not uniform, so it's not constant acceleration. Okay, well, you know what? This is actually probably an okay place to leave it. Terminal velocity we're ignoring, Raj. I mean, we don't want to complicate things with air resistance. Okay, so we're ignoring that. I'm going to leave it there. We're not going to go any more, although you can try. If I were you, I wouldn't go more than the next page, though. Okay. But what I do want to point out before I leave you is that there is a simulation that I want you to do. Let me click this. And in this simulation, you're going to be looking at a point charge. I need to pull it up. And I still have 2 minutes, so I think I'm doing okay on time. Okay, so excuse me. Where's it at? Get there, get there. Okay, so right here it is. It's called the electric potential lab. Wait, is this it? No, this is not it. Sorry, that's not it. Here we go. It's the PhET Simulation, electric potential and work. And what you're going to be doing is you're going to be plopping in a charge, and you're going to be looking at what the potential is around the charge. So right here's the website. I'm going to see. Hopefully it works. So let me know if it doesn't work. And I'm going to open that up. Come on now. Oh, here we go. So I can plop in a charge here. Make sure you follow the directions. I don't think it's a negative charge it wants you to do. I think it's positive. I can't remember. And you can actually show the E-field vectors if you want to. But what you're going to be doing is you're going to be putting equal potential surfaces around this thing. It's not letting me move. It's kind of freezing up on me. But you can hit plot, and it's going to tell you your numbers. It's going to tell you what your voltage is. 4.1. I can plot. And I can even see my grid. I can put a tape measure in here. And what I want you to do is I want you to plot the voltage versus the distance away. So I can find my distance away from this charge. Oops. Put it there. And I know what my voltage is, and so I can do voltage versus distance, okay? Don't forget to follow those directions back wherever they were. Here we go. Make sure you follow those directions, recording the constants and stuff like that. Any questions from anybody? Michael has a question. How is doing a pre-programming from just getting the equation? Okay, Michael, the truth is I really couldn't even do I guess what they call a wet lab in the classroom for this. There is one, but it's never really worked very well for me. The reason why we would do a simulation as opposed to just me giving you an equation is I want you to be thinking about this. And I saw something really interesting. Since Michael asked me a question, I'm going over my limit. If you guys want to leave, you can. But I saw something interesting on the web the other day that said that learning is a change in knowledge. And what knowledge is, it's information times thinking. And I really believe that. I think it's really good because, what is it again? Raj wants to know. It's learning is change in knowledge. Knowledge is equal to information times thinking. So truly, Michael, I could just say, hey, go on the internet and find your equations there. That would be information. You guys have so much information at your disposal. But that's not, information is not equal to, you have to think about the information. And doing this lab, doing this simulation causes you to be thinking about it. Plus then we whiteboard it and we're thinking about it more by talking about it. And that's going to really cause a change in what your knowledge state is in learning. So this was not a paid advertisement, but I do appreciate Michael asking the question. That's right, please. Physics can teach you the meaning of life. Yes, Drew, I would like you to do part 2 of the lab as well. That is similar to what we were doing just a second ago, and so you should be fine. Any questions? Okay, well, thank you very much for attending. Appreciate it. See you later.